Hey, this is Charlie Thompson, and this is the Lab 7 Practice Problems Slides How-To video. So let's get started. So the basics for Lab 7. If you want to make rain, you need to lift air up. Rising air expands and cools. Rising air cools at the dry adiabatic rate until it cools to dew point temperature at the lifting condensation level. And then, once it's cooled to dew point temperature, then the rising air is going to cool at the moist adiabatic rate. The key to Lab 7 is finding the dew point temperature. Once you find the dew point temperature, you can use that to find the lifting condensation level, and then you know at what point the parcel will stop cooling at the dry rate and start cooling at the moist rate. We'll use specific humidity to find the dew point temperature. We'll use the dew point temperature to find the lifting condensation level. So a parcel, once it starts rising, it's going to start expanding and cooling at the dry rate. As that parcel rises, it will eventually cool to dew point temperature. The elevation that it cools at is going to be called the lifting condensation level, the LCL. Once it cools to dew point temperature, the parcel will then, as it keeps going up, will cool at the moist rate. However, if the parcel sinks, it will heat up at the dry rate. So we've got two rates of cooling, depending on if the parcel has not reached dew point temperature. And then once it's reached dew point temperature, it's going to cool at the moist rate. But sinking air is always going to sink and heat up at the dry rate. And that's what causes the rain shadow effect. So I've made a template for this. It's part of the handout. Asks you to start by listing the information that's given to you in the problem. And these are the tasks, the skills that you need for this lab. You need to be able to find specific humidity. You need to be able to find the dew point temperature. You need to be able to find the lifting condensation level. You need to find the parcel temperature at the peak. And then if the parcel sinks, what's the new parcel temperature and relative humidity? So finding specific humidity, we did that last week. Specific humidity equals max specific humidity times relative humidity. If you're given air temperature and the relative humidity, that's how you do it. On the other hand, if you're given a dew point temperature, then you find the dew point temperature on the max specific humidity chart. Since the parcel's at dew point temperature, the specific humidity will be the same as the max for that temperature. Max specific humidity at dew point temperature is the specific humidity. So if I give you a dew point temperature, you just look it up and see what the max specific humidity is, and that's it. For info on finding specific humidity, go see last week's materials. Dew point temperature, same deal. We're just going to look it up on the max specific humidity chart and then find the dew point temperature across from the specific humidity. And again, if you have questions on finding dew point temperature, either ask me or go take a look at Lab 6's information. Lifting condensation level, that's new for this lab. Once we've found the dew point temperature, we can use that to find the lifting condensation level. So the parcel is going to cool by the dry rate until it cools to dew point temperature. So as the parcel is starting to rise, it's going to cool by 5.5 Fahrenheit degrees for every 1,000 feet it rises. So the first thing we need to do is find out how much the parcel has to cool by in order to cool to the dew point temperature. So current temperature minus the dew point temperature tells us how much the parcel has to cool, and then we divide that by the rate of cooling, the dry rate, to find out how many feet the parcel has to rise in order to cool to dew point temperature. So temperature on the ground minus dew point temperature tells us how many degrees it has to cool. Divide that by 5.5, and the answer is going to be given to you in thousands of feet of lifting to the lifting condensation level. It's not going to tell you the actual level. It's going to tell you how far you have to lift it to the lifting condensation level. And the units for the answer are in thousands of feet. I think that'll make more sense in a minute when we go through some examples. So we've got a parcel at 86 degrees with a dew point temperature of 77.0 degrees. What's the lifting condensation level? So temperature minus dew point divided by 5.5 tells us how many thousands feet of lifting we'll have to do. 86 minus 77 divided by 5.5. 86 minus 77 works out to 9. 9 divided by 5.5 equals 1.636. So that's 1.6 thousand feet. So 1.636 thousand feet is 1,636 feet. That's the lifting condensation level in feet. And we're going to round that to the nearest 100 feet. So that's going to round down to 1,600 feet. So the lifting condensation level, given this setup, is going to be 1,600 feet. We're going to round the lifting condensation level to the nearest 100 feet. Okay, let's do another one. So we've got a parcel at 59 degrees with a dew point temperature of 41 degrees. What's the lifting condensation level? So temperature minus dew point divided by 5.5 tells us how many thousands of feet of lifting. 59 minus 41 is 18. 18 divided by 5.5 is 3.272. So that would be 3.272 thousand feet. That's going to be 3,272 feet, and that's going to round to 3,300 feet because we're going to round the lifting condensation level to the nearest 100 feet. So the 70 rounds up, so we get 3,300 feet. All right, let's do another problem. We're going to take a parcel of air. This is also problem 1 from the practice problems. If you click there, it'll take you to the handout problems. Not the handout, it'll take you to the practice problems so you can follow along without having to write things down. So take a parcel of air at sea level to the summit of Mount Waialeale at 5,100 feet, given an air parcel with a starting temperature of 81 degrees Fahrenheit and 95% relative humidity. So we want to know what's the parcel's starting humidity, what's the parcel's starting dew point temperature, what's the parcel's lifting condensation level, what's the parcel's temperature after we're done lifting it, and what's the parcel's new specific humidity when we're done lifting it. What's the difference between the starting specific humidity and the ending specific humidity? I want to know how many grams of water vapor would actually condense as the parcel rises and cools. So let's jump in. From the max specific humidity chart, the max specific humidity at 81.0 degrees is 22.8, so that would be the max. We have 95% of that. So 0.95 times 22.8 gets us 21.66, which we're going to round up to 1/10 of a gram. So the current specific humidity for the parcel is going to be 21.7 grams of water per kilogram of air. So what's the dew point temperature? Well, we know the specific humidity. We look it up on the chart with a specific humidity of 21.7. The dew point temperature is 78.8 degrees. So now we know the specific humidity, we know the dew point temperature, we're going to calculate the lifting condensation level. So temperature, starting temperature minus dew point divided by 5.5 gives you thousands of feet of lifting. 81.0 minus 78.8 is 2.2. So it's got to cool 2.2 degrees from 81 down to 78.8. 2.2 divided by 5.5 gets 0.4. That's thousands of feet. So 0.4 thousand feet or 400 feet. It's already rounded for us, so we don't need to do anything. The units are thousands of feet, so 1,000 times 0.4 is going to be 400. The lifting condensation level is going to be 400 feet. So now we got to figure out, we know the lifting condensation level, we know the dew point temperature, so we know the parcel's temperature at the lifting condensation level, but we're going to keep lifting it because there's still a mountain. There's still Mount Waialeale up to 5,100 feet. So temperature at the lifting condensation level minus additional cooling will tell us the temperature at the summit. So the temperature, the parcel's temp at the lifting condensation level was 78.8 degrees. That's at 400 feet. So going from 400 to 5,100 feet, it's going to be rising and cooling at the moist rate because it already cooled to the dew point temperature at the LCL. So it's going from 0.4 thousand feet up to 5.1 thousand feet, and it's going to cool by 3.3 degrees per thousand feet. So that's going to work out to 4.7 thousand feet of rising times 3.3 degrees of cooling for every 1,000 feet. That's 15.1 degrees of cooling, which rounds to 15.5. The dew point temperature minus the cooling is going to give us 63.3, and that's going to be the temperature at the summit of 5,100. So now that we know its new temperature, all we have to do is look it up on the max specific humidity sheet to find out what the parcel's specific humidity is at 5,100. So the parcel has cooled to dew point temperature. As it rose and cooled, the relative humidity stays at 100%. Given a temperature of 63.3, the maximum specific humidity is 12.2, so the parcel's specific humidity is 12.2 grams. What's the difference? Well, we started with 21.7, we now have 12.2. We started with 21.7. 21.7 minus 12.2 equals 9.5 grams. So 9.5 grams per kilogram is the amount of water vapor that would have condensed as the parcel rose from sea level up to 5,100 feet. All right, problem 4, which is also problem number 3 from the practice problems for Lab 7. You can just click on the problem 3. That'll take you to the handout, or rather the practice problems sheet. Okay, in this exercise, we'll take a parcel of air up to the summit of Mount Rainier at 14,400 feet, then drop it down to Yakima, Washington at an elevation of 1,000 feet. So we're given an air parcel at sea level with 59 degrees and 40% relative humidity. We also know that the ELR, the environmental lapse rate, is 3.8 Fahrenheit degrees of cooling for every 1,000 feet you go up. And we're going to answer the following questions. What's the specific humidity of the air parcel? What's the dew point temperature of the air parcel? What's the lifting condensation level of the air parcel? What's the temperature of the parcel after it gets lifted to 14.4? What's the specific humidity of the parcel at 14.4? What's the temperature of the atmosphere at 14.4? Is the parcel stable or unstable? If that parcel of air sinks from 14.4 down to 1,000 feet, what's the parcel's new temperature at 1,000 feet? What's the parcel's specific humidity at 1,000 feet? What's the parcel's relative humidity at 1,000 feet? So for starters, what is the specific humidity of the air parcel? So we looked it up on the max specific humidity chart. Given a temperature of 59 degrees, the maximum specific humidity is 10.6 degrees. We have 40% relative humidity. So the actual specific humidity is going to be 40% of the maximum. The maximum is 10.6. So 10.6 times 0.4 is 4.24. That's grams of water per kilogram of air. So since it's a specific humidity, we round it to one decimal place of 4.2 grams. So the initial specific humidity of the air parcel, 4.2 grams per kilogram. We can use the specific humidity to find the dew point temperature of the air parcel. So again, we look it up on the chart. With a specific humidity of 4.2 grams, the dew point temperature is 33.8 degrees. So now that we know the dew point temperature, we can figure out what the lifting condensation level is. So the formula to find the lifting condensation level, or how far you have to lift it to the lifting condensation level, is current temperature minus dew point. So how much you've got to cool that parcel, divided by the dry rate, 5.5 degrees of cooling for every 1,000 feet that you lift the air. We plug that in. 59 minus 33.8 is 25.2. 25.2 divided by 5.5 is 4.581. That's, remember the units are thousands of feet, so that's 4.5 thousand feet. 4581, the 1 doesn't help the rounding. We just ignore the 1. The 8 rounds, because the 8 is more than 5, we add 1 to the 5, so we get 4.6. 4.6 is 4.6 thousand feet, which is 4,600 feet. So the LCL is 4,600 feet. So we know the temperature of the parcel, 33.8 degrees at the lifting condensation level, 4,600 feet. But now we're going to go from 4,600 feet to 14.4. So the temp of the parcel at the lifting condensation level is the dew point temperature of 33.8. It's going to rise from 4,600 feet to 14,400 feet, and it's going to cool by 3.3 degrees per 1,000 feet. So we've got 9.8 thousand feet that it's going to get lifted. 14.4 minus 4.6 is 9.8. So 9,800 feet of lifting, cooling 3.3 degrees every 1,000 feet gets us to 32.34 degrees cooler, which is going to round to 32.3 degrees cooler. The temp at the LCL was 33.8. So the current temperature at 14.4 is going to equal the dew point at the LCL minus the degrees of cooling. So temperature at 14.4 is going to be 1.5 degrees. So now we get to figure out the specific humidity. Since we know the temperature, we just look up the max specific humidity from the chart, and then whatever it says, that's what we have. So from the max specific humidity table with a temperature of 1.5, the maximum specific humidity is 1.1 grams. So now we know the new specific humidity. 1.1 grams. And the temperature of the atmosphere at 14.4. The temperature of the atmosphere. So now we have to use the ELR. So the ELR is 3.8 degrees of cooling for every 1,000 feet of lifting. That's going to be 14.4 thousand feet times 3.8 degrees per 1,000 feet is 54.72 degrees cooler. 54.7. The temp of the atmosphere, the starting temperature was 59 degrees. It's going to cool by 54.7. So the temperature of the atmosphere is going to be 4.3 degrees. So the temperature of the atmosphere is going to be 4.3 degrees. So the parcel has a temperature of 1.5 degrees. The air around it is 4.3 degrees. So the parcel is a cold air balloon, and the parcel is stable because the parcel is colder than the atmosphere. So now that parcel, after it runs out of mountain lifting it up, it's going to sink. In fact, that parcel is going to sink from 14.4 down to 1,000 feet. So to figure out how much it's going to warm, thousands of feet of sinking times the rate of warming. It's going to sink 13.4 thousand feet. It's going to warm up at the dry rate. A sinking parcel warms at the dry rate, so it's going to be 73.7 degrees warmer. 1.5 was its temperature at the summit. As it sinks, it's going to warm 73.4 degrees, so its new temperature is going to be 75.2 degrees. So what's the parcel's specific humidity? Well, it's the same as it was at the summit. The parcel warms, but it doesn't get more water. So the parcel's specific humidity is 1.1 grams. The parcel's relative humidity. Okay, so the specific humidity didn't change, but the temperature has changed. Because the temperature changed, the relative humidity changed. So the formula equals specific humidity divided by the maximum specific humidity times 100. So we look up the max on the chart. From the chart at 75.2 degrees, the max is 18.9. We have 1.1, divide that by 18.9, that gets us to 0.058 times 100. That's going to round to 6%. So the parcel's relative humidity after it sinks to 1,000 feet, it's going to be 6%. Okay, that's it for the Lab 7 practice problem slides. I wish you good luck. If you have any questions at all, please let me know. 5 minutes conversation could get you past that one part that you don't understand and let you do the rest of the problems with no problems.